All right, let's talk about directional derivatives and something related to directional derivatives called the gradient. The gradient is going to be a really important idea through the remainder of the semester, so make sure that you kind of internalize not only how to compute the gradient, but its geometric properties and how we can understand it geometrically. I want you to pay attention to all of the goals of the section. I want you to be able to compute directional derivatives. I want you to be able to compute the gradient vector. Um, I want you to understand the role of the gradient vector in directional derivatives and understanding how functions are changing. And I want you to understand that the gradient function gives a vector, it gives a direction that is perpendicular to level sets of the function. And this is true not only in 2 and 3 dimensions, but in fact in n dimensions. So the gradient is extremely important. In applications, the gradient is used to optimize functions of several variables. There are lots of really important algorithms for finding the maximum or minimum of a function of several variables that rely on the gradient. And really just an important quantity, one of the most important quantities we'll learn about in this semester. What's going on here? What's the big idea? We've learned about partial derivatives, and we know that geometrically partial derivatives tell us how a function is changing in the x direction or the y direction. But n-dimensional space, it's a big space. There's a lot of room to move, and you can always move in directions other than, say, the x direction or the y direction. What about directions in between those directions? Just to illustrate that, let's look at a sort of a generic surface. This is figure 4.39 from the section. We have this generic sort of surface sitting in 3 dimensions. It's kind of wavy and it's doing lots of things, and imagine myself, on the surface. Imagine it's like elevation or something. The steepness of the surface, or the rate of ascent or descent of the surface, is going to depend on which way I go. And if you look really closely at this, you can kind of see that if I walk parallel to the y direction, it almost looks like the surface is flat in that direction. It almost looks like if we took the partial of this surface f of x and y, if we took the partial with respect to y, it might be 0 at this point. On the other hand, if I decide instead to walk in the x direction along this grid line, it looks like the surface is dropping. So if I took the partial of f with respect to x and evaluated at AB, I would expect that partial to be negative. So in this direction, I would expect the partial with respect to y to be 0. In this direction, I would expect it to be negative. But what about this direction? What if I want to move in some direction that's not necessarily parallel to the x or y direction? How do we get our hands on the rate of change in that direction? That's what the directional derivative is for, and that's what we'll talk about in a minute. So the directional derivative is giving me information about the domain of the function. So if I'm in the domain, remember in this particular instance, the domain of this function is in the xy plane, and I'm at some point in the xy plane, say AB. I want to know what's going to happen if I move in the domain, if I change the values that I'm plugging into f in this direction, or if I change the values in this direction or this direction, right? I want to understand how the function's going to change. What we'll discover is a sort of a really natural definition using difference quotients that after a little bit of analysis we'll discover is actually a dot product. It's the dot product of the gradient with a particular direction vector. What we'll also discover, so it's really neat the way this builds. We start with the difference quotient, and then we discover that, hey, this is really just the gradient dotted with some direction vector. And then we ask, well, what's the biggest direction? What's the smallest direction of change? And we discover that the gradient actually points us in the direction of maximum change. And If we move perpendicular to the gradient, that's the direction of least change. In fact, it's the direction of zero change. What's really amazing about that is we discover that, remember how we defined level sets earlier? The level set of a function um, is the set of points for which the function is constant. If the function is constant on a set of points, it's not changing on that set of points. So what we discover geometrically is that the gradient is actually perpendicular to level sets of the function. If you want to move in the direction of maximum change of a function, you should move in the opposite direction of a level set. You should move perpendicular to a level set. And that's a really, really important geometric idea associated with the gradient. And we'll see examples of that. And it's why I added this extra, just to emphasize this extra goal up here at the top. The gradient of a function is perpendicular to level sets of the function. I added 2 and 3 dimensions because that's what we're going to be working in here, but in fact it's generally true. It's true in all dimensions. Let's do a quick flyover of the text and see how to compute directional derivatives. We begin by sort of attaching a quantity to direction. So how do we, if we're trying to define a direction, we need some way of defining direction. So we pick a point in, and we're just going to talk about functions of 2 variables right now. So we pick a point in the domain AB, and we want to understand how it's changing, how the surface is changing or the function is changing in a particular direction. So what we do is we look at a direction theta. So we always start with theta equals 0 along the positive x-axis, and we'll define, we can define all directions away from the point AB simply by the angle that direction makes with the positive x-axis. So with that in mind, with that theta in mind, this is really just all the directions that are available are really just all the directions around the unit circle. So if I want to move in the direction 45 degrees from the positive x-axis, I'm just talking about the angle pi over 4. If I want to move in the y direction, I'm talking about the angle pi over 2. So every possible direction away from AB is really just in one-to-one correspondence with some angle theta between 0 and 2 pi. So we do that, we build the difference quotient for this particular situation. We simply look at f of a and b, and we add this direction vector, cosine theta, sine theta, and then we scale it by h. And what we're going to do is we're going to let h go to 0, and what we're doing is taking the derivative of f in the direction theta. This will define to be the directional derivative. We use the notation d sub u. Capital D stands for derivative. Sub u, the u is a unit vector in the direction that we're interested in. F is the function that we're differentiating, and AB is the location in the domain where we're taking this derivative. So lots and lots of moving parts, and you're responsible for kind of figuring out how all of these things lock together. And we'll do a lot of examples here to help you get there. So this is the difference quotient definition. I'm not asking you to do any difference quotient calculations in this section. There are a couple of examples which I've omitted from your consideration at the end of the section. Don't worry about taking them by definition. I'm more interested in being able to compute them after we've sort of worked on it a little bit. If we use this definition, we can quickly rewrite the directional derivative of f in the direction u at the point xy as this expression, the partial of f with respect to x cosine theta, partial f with respect to y sine theta. We add them together and we get this. The proof is not terrible. Starting with the definition, of the directional derivative in the direction theta. We let x equal this coordinate and we let y equal this coordinate. And we use the chain rule. We take the derivative of g with respect to t. Using the chain rule, this expression immediately pops out. And furthermore, if we plug in t equals 0, we see that in fact it aligns perfectly with taking the derivative at x naught, y naught. On the other hand, if we look at the derivative of g at 0 using the definition of the derivative, we end up with exactly the directional derivative du f x naught, y naught. So on the one hand, g prime of 0 is equal to this by the chain rule. On the other hand, g prime of 0 is equal to this by the definition of the derivative. Putting the two together, we get that the directional derivative is really just this really simple expression. So if we want to find, say, the directional derivative using this alternative method, which avoids using the definition of the derivative, we can say, for example, let's find the directional derivative of this function in the direction theta arc cosine of 3/5. So what do we need in order to compute that directional derivative? We need the partial of f with respect to x and with respect to y. Those are easily computed. We learned how to do that a couple of sections ago. We also need to figure out the cosine of theta if the arc cosine is 3/5. Well, that's pretty straightforward. If theta is the arc cosine of 3/5, then the cosine of theta is 3/5. So that's where this expression comes from. A little bit trickier. What's the sine of theta if theta is equal to arc cosine 3/5? Well, now you have to build a right triangle. And 5 is the hypotenuse, 3 is one leg, and what's the other leg? By the Pythagorean theorem, it's 4. The ratio of opposite to hypotenuse is 4/5, and we learned that sine of theta is 4/5. And now it's just a matter of plugging in all the various pieces and simplifying. Finally, we were asked to find the directional derivative at the point -1, 2. So we plug -1, 2 in for x and y respectively, and we get 8. What we've learned is that if we start at the point -1, 2, and we move in this direction, we can expect the function to increase at a magnitude of +8. So it's going to increase because it's positive, and it's going to go up with the slope 8. We'll do more of these examples in a minute. Now, if you turn your head just right, and you look at this expression up here, you tilt your head just right, you look at this expression, you see that this is really a dot product of a vector fx, fy with another vector cosine theta, sine theta. We're going to take advantage of that really quite extensively. And we're going to rewrite the directional derivative again in yet a different way. And that vector of partial derivatives, partial of f with respect to x, comma, partial of f with respect to y, is so important that we actually give it a name and its own notation. We put this little upside down triangle in front of f. The triangle is called nabla, and we call it the gradient. And the gradient is simply the vector of first partial derivatives. This is a thing that you want to memorize, and we'll do a lot of calculations along those lines as well. Here we see the gradient for a function of 2 variables, but in fact it generalizes to functions of n variables. The gradient of a function of, say, 3 variables, partial f with respect to x, comma, partial f with respect to y, comma, partial f with respect to z. It's a vector with 3 components, and we can go on 4 components, 5 components, and so on. So the gradient is a very general object, and it's simply the vector of partial derivatives in each of the independent variables. Finding the gradient is really just an exercise in computing all of the first partial derivatives. For example, if we're looking at the function f of x and y, 2 partial derivatives, we expect the gradient to be a vector with 2 components. The first component will be the partial with respect to x, that's here. The second component, the partial with respect to y, that's here. All right, Carrying on, the gradient has many wonderful properties. For example, if the gradient is 0, then the directional derivative will be 0 in all directions. That'll be useful for us when we're optimizing functions, finding maxima and minima in the next section. And other properties, for example, if the if the gradient is not equal to 0, then the gradient is maximized when u points in the same direction as the gradient. This is a really powerful idea, and it's minimized when it points in the opposite direction. We can see that if we go back up here and look at the dot product definition of the directional derivative. We know that the directional derivative, boy, I just passed by it, I guess. Here, hold on for a second. Here we go. We know that the dot product is going to be largest when two vectors point in the same direction. And we know that it's going to be smallest when the magnitude will be smallest when the two vectors are perpendicular. And then we know that it'll be smallest in sign overall if they point in opposite directions. So this is the biggest possible dot product, this is the 0 dot product, and this is the biggest negative possible dot product. So what this tells us is that the gradient always points in the direction of maximum change. That's a really significant idea. It points in the steepest direction. All right, so let's look at a surface in 3 dimensions and kind of tie all this together. We're sitting here at the point x0, y0 in the domain, and we take the gradient. The gradient points in the direction of maximum change. Perpendicular to the gradient is the direction of minimum change. If we move in this direction, we're actually moving along level curves, level surfaces. We know that the level curve, for example, of this figure is going to be some kind of circular object, and moving along that, f doesn't change. It doesn't go up or down. So not only does the gradient tell us the direction of maximum increase, which is clearly going up this surface here, it tells us the direction of no change. It tells us the direction of the level curve at that point. So the gradient also gives us the tangent vector to the level curve through this point. Very important idea. Again, I can't stress enough that the gradient is giving us information about the domain of the function. It's telling us how to move around in the domain to affect maximum change or to affect no change. Finding the maximum directional derivative really just involves computing the gradient. Here we have the gradient at the point -2, 3, and then computing the magnitude of that gradient. Okay. Oh, and I should emphasize here that when you're working with the gradient, way back up here, this definition, it's really important that u is a unit vector. It's so important that we actually use the letter u to remind you that this needs to be a unit vector. And in this example down here, finding the direction for which the directional derivative is a maximum, it means taking the gradient and dotting it with, I'm sorry, hold on for a second. Okay, sorry about that. You know, there's sort of this long discussion finding the direction of maximum change or the maximum value of the directional derivative, and the authors are going through here and finding not only that the maximum value of the directional derivative, but computing the unit vector in that direction, and that's fine. We know that the gradient points in the direction of maximum change. So we compute the gradient, we plug in -2, 3, and we get this vector. They're going through the process of finding the unit vector, and that's simply taking this vector and dividing by the magnitude being, in this case, 4 root 61, which we get by just taking the square root of the sum of the squares. But we also happen to know that the magnitude of the gradient of f at -2,3 is the rate of maximum change. So that magnitude is 4 root 61. This tells us how to move in the domain, which direction to move from the point -2,3. We move in this direction. And if we move in that direction, we know that the surface will be increasing at a rate of 4 root 61. Cool. All right. Gradients and level curves. What we know is that the gradient, let's look at the gradient of, say, this surface. These are level curves. Let's say we're sitting right here at this point, the point 1, 0 in the domain. Which way is the gradient going to point at this location? It's going to point in the direction of maximum change. So it's going to point parallel to the x-axis because that's the direction that's going to go up most quickly. And you'll notice it's perpendicular to this blue curve. So that's just reaffirming this notion that the gradient points in the direction of maximum increase. So finding tangents to level curves really means finding the gradient, getting that direction, and then finding some perpendicular direction. For example, if we want to find a tangent to the level curve at the point -2, 1, the first thing we have to do is figure out what's the value of f at -2, 1. And honestly, let's just carry on here. The value is going to be 18, so the level curve is going to be this ellipse that you get by setting f of xy equal to 18. We compute the gradient, f sub x, f sub y, and we plug in the values -2 and 1, and we get this vector, -9i plus 18j. This vector will point in a direction that's perpendicular to the level curve at the point -2, 1. If I want a tangent vector, what I do is switch these two components and change the sign on one of them. So we exchange the roles of -9 and 18, and we change the sign on the 18. We could have also changed the sign on the 9. That gives us a direction tangent to the level curve at this point. So just to repeat, gradients are perpendicular to level curves at the point. We get the gradient, we want the tangent vector, we just, in 2 dimensions, we just swap the coordinates and change the sign on one. In 3 dimensions, it's a little more complicated, right? Because yes, the gradient will still be perpendicular to the level surface, but there's going to be a lot of tangent vectors that are perpendicular to the gradient. And actually, the book goes on and talks very briefly about 3-dimensional gradients. You can see it's just the vector of first partial derivatives for each of the independent variables. And finding those gradients is just a matter of computing those and plugging them in. You can ignore definition 4.41. I'm not super excited about this. This tries to take the same idea from 2 dimensions up to 3 dimensions, and I don't think it works very well. So in fact, you can ignore really from 441 on down, and I'll try to emphasize what you should be paying attention to as we work through the exercises. So let's work through some of these exercises. Okay, the first couple of examples, we're asked to simply find the directional derivative of the function at the point P. In the direction of v, function h, and we're given the direction v. So these are essentially computational problems just to kind of get you used to this notion of finding directional derivatives. So in problem 264, we're given e to the x sine y, and we're given a point, 1 and pi over 2, and a direction, -I. If we want to compute the directional derivative, the first thing we need to do is compute the gradient. So in 264, oops, I don't want red, I want black. In 264, we compute the gradient of h, and that's the vector. There are two independent variables, so we're just going to look at all of the first partial derivatives. The derivative of h with respect to x is e to the x sine y, and the derivative of h with respect to y is e to the x cosine y. Now, we want to know what the gradient is at this particular point in the domain. So we write the gradient of h evaluated at 1 pi over 2. And we plug in x equals 1 and y equals pi over 2. When x is 1, we get e. When y is pi over 2, the sine of pi over 2 is 1. Again, e. And then the cosine of pi over 2 is 0. So this nets out to 0, and that is the gradient of the function h at the point 1 pi over 2. To compute the directional derivative, we need to dot this with a vector in the v direction. So we need to dot with a vector, a unit vector, sorry, in the v direction. Well, the v direction we've been given is this vector, -1, 0, like that. What's the length of this vector? Well, it turns out the length of v is already 1. So this is already a unit vector. So it remains to just compute this dot product. So the directional derivative in the direction of -I of h evaluated at 1 pi over 2 is e0 dotted with -1, 0. And that turns into a scalar, -e. And what we know now is if we stand at the point 1 pi over 2 in the domain, and we look in the -1, 0 direction, or we move in that direction, the values of h are going to be decreasing. Let's go look at a GeoGebra example to see this visually. So in this GeoGebra example, we have the positive x, positive y, positive z axes. We have the surface, e to the x sine y. It looks like this. We're interested in the point 1 pi over 2 in the domain. So that's down here in the domain, a distance 1 unit out along the x direction and pi over 2 units out in the y direction. And we're interested in how the values of the function are changing if we move, let's remind ourselves, if we move in the v direction, -1, 0. So I'm standing here and I'm asking myself, which direction is the -I direction? That's in the direction of the negative x-axis. So that's this. All right, so if I move in that direction, let me turn that vector on. What do we see happening up on the surface? Well, we're down here at A, we go up to the surface and we move in this direction away from A. We can see clearly that the surface values are going to be decreasing. They're going to be going down this slope if I move from A in this direction. And that's exactly what the directional derivative is telling us. The directional derivative of h in the direction -I at the point 1 pi over 2 in the domain is -e. There's a lot there, and make sure that you can unpack every piece of that statement. Just to do another one in 3 dimensions, which is harder to visualize but no less important, 265. We have a function of 3 variables, x, y, and z, and we want to compute the directional derivative at the point 2, 1, 1 in the direction 2, 1, -1. First thing we need is the gradient. The partial of h with respect to x is yz. Partial of h with respect to y is xz. Partial of h with respect to z is xy. We want to evaluate that at the point 2, 1, 1. Plugging in x equals 2, y equals 1, z equals 1. We get 1, 2, 2. And we need to look at v. V is not a unit vector. To construct a unit vector, we need the magnitude of v. The magnitude of v is 4 plus 1 plus 1 square root of 6. So the unit vector that we need in order to compute this directional derivative is 1 over root 6 times the vector 2, 1, negative 1. Everything's now in place. We're ready to compute the directional derivative. The directional derivative in this direction u of h at the point 1, 2, 2 is simply the dot product of these two vectors, 1, 2, 2, dotted with 1 over root 6, 2, 1, negative 1. The 1 over root 6, it's a scalar. It's just going to go along for the ride, so we'll write it in the final answer. And now the dot product of these two vectors, 1 times 2 plus 2 times 1 minus 2 times 1. So that's just 2, and we get 2 over root 6. What this tells me is for this function x, y, z, if I'm at the point 2, 1, 1 in space now, in three-dimensional space, and I move in the direction v, the rate of change is going to be positive, and it's going to be 2 over root x. So we could expect the function values to be increasing if we move in this direction. Harder to visualize, but no less important. Here we're asked to find the directional derivative of the function in the direction of a unit vector of the form cosine theta sine theta. Honestly, this is a bit of a step backwards in the section, but I thought it was worth covering just the same. So we're asked to find the directional derivative in this direction theta. What that means is you want to find the unit vector cosine theta sine theta. For theta equals pi over 4, that's root 2 over 2, root 2 over 2. This is a unit vector. It's a unit vector by design because cosine squared theta plus sine squared theta is 1, square root of 1 is 1. To compute the directional derivative, of course, we need the gradient of this function. The gradient is going to be minus sine, it's going to be the vector. The first component of the vector is the partial of f with respect to x. That's minus sine 3x plus y times the derivative of what's inside with respect to x. So there's an extra factor of 3. And then the second component is the partial of f with respect to y, also minus sine 3x plus y times the derivative of what's inside with respect to y, a factor of 1. We can simplify this a wee bit. We can factor out a sine 3x plus y. In fact, we can factor out a minus sine 3x plus y. And what's left behind is simply 3, 1. So that's the gradient. We want the directional derivative not at any particular point, but at the general point, x, y. So we don't have to plug in any x or y values. We simply have to compute the dot product. So the derivative in the direction u of f at the point xy is this dot product, sine 3x plus y. That's a scalar, 3, 1, dotted with root 2 over 2, root 2 over 2. Computing this dot product, we have 3 root 2 over 2 plus root 2 over 2. That's 4 root 2 over 2, aka 2 root 2. And that is the general directional derivative at the point xy. A little bit of a change up here. Compute the directional derivative of the function at the point P in the direction of Q. So we've got some point P sitting out here in space, and we've got some other point Q sitting out here in space. We want the directional derivative at P if we go towards Q. That means we have to compute the vector PQ, which we learned a couple of chapters ago. We learned to be 4, 5. Sorry, let's focus on the problem at hand. So we take Q minus P, minus 1, 2, 0, minus P, 2, 1, negative 1. We subtract component-wise. Negative 3, 2 minus 1 is 1, and 0 minus negative 1 is 1. So that is the direction that we're interested in going. Of course, we need the unit vector, and this is not a unit vector as it stands. The magnitude of PQ is 9 plus 1 plus 1, so what's that, 11? Square root of 11. So the unit vector that we have to use for the directional derivative is 1 over the square root of 11 minus 3, 1, 1. So we've got the unit vector direction taken care of. We now need the gradient of f, and that's the vector of first partial derivatives for each of these 3 independent variables. The partial of y over x plus z with respect to x is going to be minus y over x plus z quantity squared. I'll ask you to check that on your own. The partial with respect to y is simply 1 over x plus z. And finally, the partial with respect to z is going to be minus y over x plus z quantity squared. That is the gradient. We want to evaluate the gradient at the point in question, in this case P, which is 2, 1, negative 1. So the gradient of f at 2, 1, negative 1. So we're plugging in those values for x, y, and z respectively. In the first coordinate, y is 1, so we have minus 1. And we have x plus z in the denominator. X plus z is 2 plus negative 1. That's 1. And notice we see x plus z appearing in the denominator all the way across. So conveniently for us, these are all 1s. So to evaluate the gradient at 2, 1, negative 1, it's really just negative 1, 1, and negative 1. So now we have the gradient vector at the point, and we have the direction in terms of the unit vector u at the point. The directional derivative in the direction u of f at the point 2, 1, negative 1 is the dot product of negative 1, 1, negative 1 with the unit vector 1 over the square root of 11, negative 3, 1, 1. Computing this dot product, we do the pairwise products. We get 3 plus 1 minus 1, so we get 3 over the square root of 11. So again, very difficult to visualize, but if we were in the domain of this function at the point 2, 1, negative 1, and we moved in this direction u, we would expect the function values to increase in that direction. Okay, in problem 298, we're given another function of 3 variables and a point, and we want to find the direction. at this point in which the function increases most rapidly. And this leverages the fact that the gradient at a point is the direction of maximum increase. So to answer this question really means just taking the gradient and computing its magnitude. All right, so we compute the gradient. That's the vector of first partial derivatives. The partial of this thing with respect to x is 1 over y minus z over x squared. We have an x in this term and we have an x in this term. And we have the partial with respect to y, so that's minus x over y squared plus 1 over z. And last, the partial with respect to z, we have minus y over z squared plus 1 over x. We are interested in the gradient at the point 5, negative 5, and 5. Carefully evaluating, we have y is negative 5, so we have negative 1/5 minus z over x squared, so that's 5 over 5 squared, so that's 1/5. In the second coordinate, we have 5 over 5 squared? Negative 5 over 5 squared. So that's negative 1/5. Plus 1/5. And in the last coordinate, we have 5 over 5 squared, so 1/5 plus 1/5. Simplifying a bit, we get negative 2/5, 0, and 2/5. That is the direction in which the function increases most rapidly, and the derivative in that direction is simply the magnitude of the gradient. And the magnitude of the gradient here is 4/25 plus 4/25 square root. That's going to be 2 root 2 over 5. All right, so in that direction, we can expect the rate of change of f to be 2 root 2 over 5. Alrighty. In the following exercises, or in this exercise number 302, we want to find the equation of the tangent plane and the normal line to the given surface at the point. Once again, we have a function of 3 variables, and we have a level curve. This is not a level curve, this is a level surface. Bit of a typo there. And what do we know? We know that the gradient at a point is perpendicular to level sets, the level set containing that point. So let's look at this point 2, 2, 2. What happens when you plug 2, 2, 2 into the expression for f? F of 2, 2, 2 is equal to 4 times 4 minus 2 times 4 plus 4. That's 16 minus 8 plus 4, that's 12. So 2, 2, 2 is on the level set corresponding to c equals 12, which is exactly what's indicated here. We're just kind of double checking that. All right, well, we've verified now that this point 222 is on the level set corresponding to c equals 12. Let's compute the gradient of f. The gradient of f, partial of f with respect to x is 8x, with respect to y is negative 4y, and with respect to z is 2z. At the point 222, we see that this gradient points in the direction 16, minus 8, and 4. Points in that direction. If we want to build the tangent plane at that point, what do we need? We need a normal vector and a point. Well, we know this is the normal vector because gradients are perpendicular to level curves or level surfaces. So this is normal to the surface at 222. So we can use that as a vector n in the construction of a plane. What point should we use? We use the point of tangency, 222. So the equation of the plane, the tangent plane, is given by 16 times x minus 2 minus 8 times y minus 2 plus 4 times 0. That's the equation of the plane. What if we want the normal line? The normal line, we have the information we need there as well because we have a vector that points in the normal direction and we have a point on the plane. So the normal line at this point is simply in parametric form the point that it passes through, so 222, plus t times the normal direction, 16 minus 4y and 2z. Now to help you visualize this and convince you that the gradient is always perpendicular to level surfaces, I've got another GeoGebra example, so let's pull that one up. Oops, this one here. Okay, so here is the surface, the level surface. So if I take this function of three variables, f of x squared minus 2y squared plus z squared, and I set it equal to 12, what I get is a surface in space. And at every point on this surface, at every point on this red surface, the value of the function is 12. Let me put the point 222 on the surface. So that's this blue point A, and it's, as I rotate it around, oops, I can see that it sits right on the surface. All right. And let's light up the plane that I just computed. This plane has a common factor of 4 in each of the components, so I just divided by 4. 0 divided by 4 is 0. This turns into a 1, this turns into a 2, this turns into a 4, and I just put that plane into GeoGebra here. Okay, and if we move this around a little bit, we can see that indeed this plane is tangent at the point A. This is a challenging idea, and it's one that I want to spend just a brief moment talking about. This is, in some sense, a single slice of this scalar valued function, right? The function is defined at every point in space. If I plug in a point in space, I'm going to get a number out of this. The points that are here on this surface happen to be the points that give the value 12. But if I look at the whole family of these surfaces, right? So this slider changes the 12. It moves the 12 around. What I see is I'm kind of moving through space and I'm creating additional surfaces for different C values. It's really hard to see, really hard to imagine, but you can kind of see it, the surface in here closing in as I take the C value down to -5, and as I increase it, we can see it expanding. When it gets to 12, it matches the surface exactly, and then as I go past 12, that level surface is now outside of the surface corresponding to 12. So this is kind of a really curious slicing of space, and what we're interested in is the slice of this function where the C value is 12, and then we're interested in the tangent plane at this point 222 that happens to lie on this level surface. A lot of moving parts here. You're going to have to really dwell and think about this to get it safely into your head. Okay, one last little applied function. We have the temperature T in a metal sphere is inversely proportional to the distance from the center of the sphere. So the first thing, and you're asked to find the rate of change of the temperature at the point 122 in this direction, and then show that at any point in the sphere, the direction of greatest increase in temperature is given by a vector that points towards the origin. So the first thing you want to do is build an expression for T. T is a function of three variables, x, y, and z, and we know that it's inversely proportional to the distance the point is from the origin. So that's the square root of x squared plus y squared plus z squared. You're given a little bit of information. You're given that the temperature at the point 122 is 120 degrees. This is going to let me solve for k. So we know that T at 1, 2, 2 should equal 120 degrees. On the other hand, by the inverse proportionality relationship, it must equal 1 squared plus 2 squared plus 2 squared, like that. Now we have an equation in k that we can solve. The denominator of that equation is the square root of 1 plus 4 plus 4, aka the square root of 9, aka 3. And we get 3, we get that that's equal to k over 3. Solving for k is equal to 360. And we can take that and definitively now express T with no constants. Find the rate of change of the temperature at the point 122 in the direction 213. That sounds a lot like a directional derivative problem. So in A, we want to compute the directional derivative in the point 213, in the direction of the point 213. So let's call this P and let's call this Q, just like in that earlier problem, and let's compute the direction from P to Q. That's 2, 1, 3 minus 1, 2, 2. That's out to 1, -1, and 1. That's not a unit vector, and of course we need the directional derivative in this direction. So we normalize this by dividing by the magnitude of this vector. The magnitude of the vector is the square root of 3. And that's the u that we'll use in the directional derivative. What's the next thing we need? We need the gradient of this function t. Let's compute the gradient of t. That's going to be 360, that scalar just comes out front, times the derivative of what's inside. It might help you as you're computing this derivative to rewrite this as the square root, as x squared plus y squared plus z squared raised to the 1/2. Now we can take the derivative. We're going to get a 1/2 times x squared plus y squared plus z squared to the -1/2. And then don't forget the chain rule times the derivative of what's inside, 2x. by the symmetry of this expression, we get 1/2 x squared plus y squared plus z squared to the minus 1/2 times 2y, and finally 1/2 x squared plus y squared plus z squared to the minus 1/2 times 2z. You run into these radially symmetric functions a lot in physics and in engineering, and they do have some nice properties. If we pay attention closely, we see that this 1/2 cancels with 2 all the way across. That's a pretty common phenomenon in these radially symmetric expressions. And furthermore, we see a common factor of x squared plus y squared plus z squared to the negative 1/2, which we can factor out as a scalar. So pulling that out, we get 360 divided by the square root of x squared plus y squared plus z squared. What's left behind is a pretty simple expression, x, y, z. All right. We want to compute, we want to know the gradient not at a general point x, y, z, but in fact at the particular point 1, 2, 2. So we compute the gradient of t at 1, 2, 2. Substituting in the denominator here, that's the square root of 9, 3, so 360 over 3. And then x, y, z is just 1, 2, 2, like that. 3 goes into 360, 120 times? And there we have the gradient at 1, 2, 2. The directional derivative, the last step, is denoted directional derivative in the direction u of f at the point 1, 2, 2 is simply 120, 1, 2, 2, dotted with, and what was that u vector? It's up there, 1 over the square root of 3, 1, negative 1, and 1. Let's do that dot product. That's 120 over the square root of 3. 1 times 1 plus negative 2 plus 2 is just 1. And that is the rate of change of the temperature if we are at the point 122 and we move in the direction of the point 213. Okay? And show that at any point in the sphere, the direction of greatest increase in temperature is given by a vector that points towards the origin. All right. All right, you'll notice I paused there because in part B, I'm asked to show that at any point in the sphere, the direction of greatest increase in temperature is given by a vector that points towards the origin. And looking at my gradient function, I see a function that is not pointing towards the origin, but in fact is pointing away from the origin. At every point, x, y, and z, right, think about x, y, and z as being the tip of the vector with its tail at the origin. That direction is always away from the origin. No matter where I am in space, it's away from the origin. And so I was a little bit confused because I can't show that. So it got me looking back over my work, and I realized that I made a mistake here. This expression right here, and some of you may have caught this, should be minus 1/2 when I use the exponential form. And so that changes things a wee bit. So I'm going to go through and try to make those changes without messing too many people up here. My k is okay. I didn't mess that up. But when I come down here and make these and do these partial derivatives, there should be minus signs because I take the minus 1/2 down, and then each of these should be minus 3/2 instead of minus 1/2. And then carrying on with this, that should then come out front as not a square root, but in fact the denominator is to the 3/2, and there's an overall minus sign that comes out. Okay, continuing with this process, we put the minus sign in there. What is this expression at 1, 2, 2? Okay, so 1, 2, 2, we get 9 inside. Square root of 9 is 3. Cubed is 27. So this 3 is actually a 27. So that's 360 over 27, aka what, 120 over 9, 40 over 3. So that reduces down to 40 over 3, carrying through the minus sign. And I think we're good. Put a 40 over 3, a minus 40 over 3 here. And minus 40 over 3 root 3 here. Okay, so that fixes that problem. Apologies for the mistake, and it also fixes part B. Here, and I'll just put part B right here, we see that because of the minus sign, means that we're pointing towards the origin. At every location. The minus sign redirects that vector. So this vector xyz has its tail at the origin and its head at this point xyz. When we multiply by -1, that vector points in the opposite direction, and that's towards the origin. Okay, for the exercises, don't bother with 260 through 262. This is finding the directional derivative by definition, and I don't want you to deal with that. And for web work, when you feel comfortable with the ideas, jump over to web work and try Chapter 4, Section 6. Thanks a lot.